This is our bending stress uh, presentation using 3-point flexure testing on ITAM.
I'm Lena. Our objective during this lab was to demonstrate how flexure is studied in a laboratory setting and derive a deflection model out of it. The procedure contained a 3-point flexure testing of a acrylic sample, and during the same time, we read the force and displacement from the gauges. Our takeaway was a deflection depends on force amount and setup of the sample. To comprehend what a bending stress is, it's the amount of pressure within the specimen that is being bent along its neutral axis. It is given by torque and distance from neutral axis over respective amount of inertia. Um, for the lower radius, stress is compressed, and for the high radius, it is tensed. What a 3-point flexure is, it's about putting the sample between two supports, and the load after is applied directly in the middle of the sample. It is the simplest to set up within boundaries of the laboratory, and is the maximum moment is given by 1/4 of the product of force and support lane.
Preparation methodology. A sample of acrylic is fitted with a sensor, then flexed on a semicircle of foam that has a given radius. That's to verify the strain error and to verify that the sensor works. If the sensor works, then the sample is placed onto the two pins with the probe lowered slightly until contact, and a video is recorded to keep track of all three gauges, the voltmeter, the strain gauge, and the force gauge. Data processing is done by having 100 equal parts of the length. The first 50 are used to model it, and then the results are mirrored at x equals after x equals 1/2, and the numbers are plugged into this equation. The force and displacement obtained from the video is used to create a force displacement graph. Load displacement shows the bending stiffness, and the bending stress and strain graph is made from taking the bending stress and strain from the voltage, and that's used to find the Young's modulus in the sample as well. The linear regions are used. The linear regions are analyzed in Excel to find a linear regression for the both of them as well as a slope. Here are equations that we used. Some of them consist of finding the output voltage. The input voltage is given of 10 volts. The percent difference is to verify that the sensor works. The moment of inertia uses the base, which is wide, the height, which is low, and the Young's modulus sample used for the calculations is from the force displacement graph. Here are results and analyses. On the right is our bending stress versus strain graph. On the left is our stress versus strain graph. On the right is our force displacement graph. And in the table is our two Young's moduli that we found. We used the one for, as I said before, the one from force displacement for our calculations. And here are the error percentages compared to the textbook value of acrylics Young's modulus. Here's our volt versus displacement graph. It's linear as expected, since as the voltage goes up, the strain goes up as well. And the strain is the ratio between the original length and the original and the new length increment And here's our deflection function graph, which shows the behavior as expected.
The bending stress versus strain graph and the force versus displacement graph both showed a clear linear elastic behavior in the initial leading range. The stress strain slope indicates a modulus lower than the typical steel, which is 200 GPa, and that's because our sample was made out of acrylic. The low displacement trend showed consistent, smooth data, which is an evidence of proper test alignment and strain gauge bonding. For our conclusion, we have successfully conducted a 3-point bending test. We demonstrated how a strain-related voltage convert to measurable strain and verify the linear relationship between stress strain within elastic region. Our results are consistent within the theoretical flexure equation and confirm accurate data in the analysis. We have determined the bending stiffness and the Young's modulus. For future work, it is better to use a more refined sampling to minimize the noise in the strain reading. Perform multiple tests for accuracy and use DIC, just like the previous labs, and maybe repeat the tests at different temperatures to evaluate the thermal effects. Our references were both RTAs, Hengama and Shrupa, the handouts during the lab, the flexure and strain measurement handout, MathWeb, Touchstone Testing Laboratory, and STC Verifier.
That is it.